one hand, and then H is simply N times the current over here. Number of turns times the current.
Mu was length times what? What was mu again?
Oh, the mu, that will be an average slope of this line. So what you have to really do is integrate this over time, and depending on how much time you spend in each location, you're going to be observing different mu's over there.
Okay.
So that mu has to be integrated over time, average over time. You know, that's a very yucky equation. So you just basically take this slope, and it's approximate.
Okay. Thanks.
And that's what
So
the
do you
mu
use
is.
slope then?
It's the slope of this line.
So what?
What's the slope of that line? Mu. Awesome. Thanks.
Okay, but let's imagine that we don't want to look into the transformer right now.
Do you
And
remember
good rule of thumb, it is not necessary to do it this way, but what we do
Didn't?
is
I said you
keep
did.
this as a percentage of the maximum current that is flowing through there. Okay? Or maybe not the maximum, but some kind of an average over here, if this was flat completely. So take an average of just the upper half over here. Make that 10% of that, and that's a good design for the forward converter. So if we look at what that value on average would be in here, we know that it goes to, that current at peak value goes to N times IS. We can even use that value here, make that 10% of this, and that's going to give you quite a good idea for delta IP. So you just want to make it easy, not hard. So you do N times IS, 10% of that should be the delta IP. And this is a heuristic in here because you can do it the other way too. But that works.
Is that the equation you're comfortable with us using on the test?
Yeah.
Okay.
And the question in the book was going completely the other way because this is a design question where we are calculating the values for the inductances, and in the test, in the quiz, you had those given and you had to calculate some other things about the circuit. Calculate the voltage and current. We kind of gave ourselves the voltage and current because that's our design criteria. So to find out what the L1, good value for L1 would be, good meaning not too big, so it's too expensive, and not too small, so we have too much magnetization in the core compared to, or it is not really magnetization of the core, it is how well are you using the transformer you have. Because if you do it this way, about 10%, then it would be hardly even possible to push more power through that core. So given the size of the core you have, there is a limit to how much power you can go through with this circuit. And that's when you use this equation. That's going to be almost optimized at that level there. So then L1 here will be V1 KT divided by this delta IP. So let's calculate this number first, delta IP. It's N times IS. IS is peak value there. So it's 2.5 and 10.2, and we can add to this 25, 2.5%. So we have 10.4 multiplied by N, which is 10.2. So that's 106 amps. Yes?
What happened over there? You did all that in your head like crazy fast.
Oh. I'm trying to figure out IS.
Okay.
So I look over here, that IS is this point,
Mm-hmm.
which is N times Is is this point. So I have 10.2 amps, which is right there, and I have to add 2.5% to it to go up to here.
Ah, okay, thanks.
So that gave me 106 amps for this point. Accidentally became exactly the same number as in the quiz.
And then 10.2
And then I
is
take
also
10%
our,
of that,
and 10.2 is also our turns ratio, right?
and it's accidentally, this is also 10.2.
Okay.
That value. It's pure accident. Really. So it's 10.6 amps over here.
104.
10.6 of an amp for that delta IP. So now I have 24 volts, 0.4 for the duty cycle, and we have 100 microseconds.
106. 10.4.
And divide this by 10.6 now. Times 24, times 24,
Oh, then 10.
times
Yeah, I got 106.
We have 90 microseconds, henries. 90 microhenries. So look at this. This is only 90 microhenries. And that one ended up being 11 millihenries. Let me verify because that looks too optimistic for you. 90, 24 volts times 40 microseconds divided by 10.6. Yeah, 90 microhenries.
Does that, because we just use the top, we just use the 2.5% for the upper, yeah, so it was just kind of, it wasn't really delta IS, right? That was just the top, that was IS peak, right?
Yeah, I just used the IS peak in here because that's the value that I could calculate.
Okay,
I could have tried to make it an average value in here, but I would have an equation where delta IP is on both sides of the equations, and I would have to
Sure.
calculate it more.
so that's just kind of like worst case scenario then?
It's just a rough estimation, really,
Okay.
because the 10% is off the wall anyways, so that's could be anywhere between 8 and 12% maybe.
Okay,
So that would compensate for all those changes in here.
thanks.
I just use the value that's easy to get.
Okay,
And that tells us that 10.6 amps will be also this current, right? That's 10.6 amps. So, the current I1 is going to have a ripple on its own, and it's going to be a pretty big ripple. Output ripple is low, input ripple is pretty big, because we have all that square wave on it, right? So normally you would have to use a capacitor in here, because you don't want to pull this from the source like that. And then the ripple, that's why we always calculate the RMS value of I1, because that RMS value of I1 will be used to select the proper capacitor. It has to be able to good enough to sustain an RMS of AC going through it, because the capacitor is heat up because of the RMS current. So you choose big capacitance over voltage because you want better life. So you go with 48 volt capacitor in here, 36 more than what this is. But also you have to take into account what the RMS value is allowed, and that's going to be mainly the size of the capacitance that determines that. Electrolytic capacitors or film capacitors usually are used in this place. I guess that's really all we have in here. We can ask the question about the resistance value here. 98 divided by 10.2, that's 9.6 ohms. We could figure out what would we want to use for this capacitor to have certain ripple of voltage at the output, because because that's not even shown here. But that's less of a problem really, because that capacitance, for the most part, make as big as you can possibly make it, right, for most of the stability of the atom. Unless that's going to cause a problem with the control circuit. Once you start controlling the duty cycle, big reactive components like this, they cause you, the dynamics of the system is going to start slowing. You cannot control it, you have a giant capacitor at the end.
Yeah.
So then you can probably, instead of using one capacitor like this, go with a multi-level stage of filtration. And that makes it even harder for the control system, but you can modify the dynamics in which those poles coming from there become insignificant. It's not the dominant pole of the dynamics anyways. And it's easier to accomplish your filtration with fourth order stage, because with the fourth order you can make quite a drop, right? And with the second order, the levels of dB per decade is only 40, right?
Mm-hmm.
So you could organize your poles in here to make this into some kind of a response like this, where you have that kind of a filter, a Chebyshev filter, and then that will work nice.
Since the load is so small, though, I mean, resistance-wise, it should react fairly quickly, right?
Well, since that resistance is so low, you're going to have to use giant capacitance to accomplish the ripple reduction. So the RC is what counts. If you reduce R, C is increasing, and the time constants are what's driving the filtration. With the 10 kilohertz switching, if you're driving, I don't know, if you're using this for a power supply or something, you want to have the fastest possible response you can. So you want to have the dynamics of the control system go up to almost, it's hard to make it maybe 1 kilohertz would have to be the response dynamics, right? So that your control system could be making changes at 1 millisecond rate. So if the capacitor at the output is not at 98, but it's at 95, then it's going to bring it up within, a millisecond time. That's possibly doable. But with 10 kilohertz frequency, that's pretty much, all you can do. You can increase it to 100 kilohertz, and then you can make it much faster.
Mm-hmm.
So that's another benefit of having higher frequency of switching. So normally, kilowatts are going to be run at 10 kilohertz. Below that, hundreds of watts you can easily go into higher frequencies. The difference is ferrite core. There is a limit on your density of flux, so ferrite core cannot hold as much power as an iron core. But the iron core, there's only, you have to slice the core into thin sheets, and they have to be laminated so they're not conductive. And there's only, you can make them paper thin, but there's a limit to it.
Yeah.
And that limits your frequency of operation to a certain maximum. 10 kilohertz is doable. Maybe even 100 kilohertz if you have some kind of technology, but that's going to be a very expensive transformer.
On your diagram at the bottom, right, with VI, the step in the middle, is that like arbitrary, or is there necessarily a time and period that's going to happen?
This point in time here, or maybe this, will be it will be longer if the inductor is bigger or smaller. Let me see. If you increase that inductance compared to this inductance, then you have that's bigger. So this is bigger, right? So So you're going to have L3 over L1 times KT. So if you make them exactly equal, then this time is equal to this time. So that's the leftover from the period. And sometimes you want to do it because, you know, this winding here may be still fairly large. If you don't have enough room, you might want to prefer to, you know, use much thinner wire and make more turns in here or do stuff like that. You can adjust what kind of level of voltage you would want to have, but then you cannot use the same voltage V1 to operate. You have to have a separate voltage for it to dump this magnetization. If the out is available, then that's a perfect place to dump it, because then you're helping with power conversion. You have the forward converter and flyback converter at the same time. Because if you disconnect it from here and put it over here, forward phase is this, and then you have the flyback phase that is that. So we go into more advanced, different, there's this Weinberg converter that is very interesting. It acts both as forward and flyback. So look like the forward converter one more time. But as I said, you know, that's not a very trivial example. You can maybe go through calculations of the flyback next time, I don't know, for the test, or you are going to be more comfortable with that one already. So we'll figure it out on Monday. This is what I'm, you know, thinking about. I'll arrange this differently, but that's going to be the forward converter to calculate some stuff.
So, our business was,
When is it? The 23rd?
a week from today.